All right, so in this lesson, yeah, I know it's 5.2 at the top. I pulled these notes from somewhere else because I really, really liked them. So even though it's 5.2, yes, I know technically this is actually lesson 5.4. Okay, in this lesson, we're going to talk about the first derivative test. Now, you got a sneak peek of this on your own paper in the lesson video from 5.3. But we're going to dive into more of how to use it to determine how a function behaves. Okay, so before we get into this, just a couple quick review things here. So if you are given a curve of a function, right? Remember, first of all, critical points. These are potential points where there are maximum and minimum values. Another way to look at it, it is where the derivative of the function is equal to 0. So remember, derivative is slope. So I'm going to go through and think through, okay, where are the points on this graph where the slope is 0? So here's the first one at the top of this hill. If I draw a tangent line, it's clearly flat, which means I probably have a critical point at x equals 3. Okay, and then I can keep going, and there's another one here. All right, so I know x equals 5 is another one. And then remember, critical points are where the derivative is 0 or the derivative is undefined. So it is undefined at this sharp corner right here, x equals 6. Okay, so I got 3 critical points, 3, 5, and 6. And I want to try and figure out, well, what is this function doing um, in and around those critical points, right? So in the last lesson, we set up a chart very similar to this. I can take the interval before 3, in between 3 and 5, in between 5 and 6, and then after 6. And I can use the derivative of this function to figure out what is my function doing. Okay, so in this first interval, all right, from negative infinity all the way up to 3, if I think through just this interval right here, and I look at my function, and I take different points on my function and think through what is the derivative at every point along that interval. Well, the derivative is positive. Okay, I have a positive slope. All right, and I can do that for all of these intervals. Once I hit 3, I know I'm flat, so here's my critical point right here. And then from 3 to 5, my derivative is negative. The slope is going down. Okay, I have a critical point at 5. Then I look at this interval between 5 and 6. I have another positive interval, or a positive slope, I should say. And then I hit my critical point. And then from 6 on to infinity, it looks like I'm going back down. I have a negative slope. Okay, now, review from the last lesson. How does this help us? Well, the sign of the derivative, positive or negative, tells us whether or not the original function is increasing or decreasing. And putting that together with the critical points, I know that if I have a graph going from a positive slope to a negative slope, this creates a maximum value. So I could say that x equals 3 is a maximum value. Okay, then if I have along the next critical point, if I have an interval going from negative to positive, this is a minimum value. So x equals 5 is a minimum. And then from positive to negative again, this is another maximum value. Okay, now you might be thinking, well, yeah, that's really easy to tell from this picture. The first point right here is clearly a hill, so it's a maximum. The next point is a valley, so it's a minimum. And then again, we're on top of the hill again, so this is a maximum. However, what if you weren't given this picture? What if you were just given a function and you had to figure out how that function behaved? This is where the first derivative test comes in handy. And once again, the first derivative test is this table right here. Okay, so this table that we set up is the first derivative test. All right, now, so here's an example like I was just talking about. You're just given a function. You are not given the picture. You're actually told to sketch the picture based on the function. Now, of course, there's graphing calculators that exist in the world, um, but in calculus, the study of rates of change, remember that's how we defined calculus at the beginning of the year. The study of rates of change says that you should be able to describe how a function behaves, even if you don't have access to its picture or its graph, or if you don't have a graphing calculator on hand. So here I've got f of x equals x cubed minus 3 halves x squared plus 2. And I'm going to try and describe its motion or draw its picture. Okay, so the first step in all of this is determine the critical points. So step 1, critical points. And remember that is where the derivative is equal to 0 or it is undefined. So the first thing I need to do is I'm going to take the derivative of this function. And I'm going to get 3x squared minus 3x, just like that. Okay, and then to determine the critical points, I am going to set this equal to 0 and try and solve it. So when I do that, I end up with something like this. Let's see. Okay. Oops, not 0. 1. All right. There's one critical point. Okay. Another way, there's actually 2 here, so be careful. Another way I could solve this quadratic is by factoring this. All right. So if I factor this, I get, let's see, 3x times x minus 1. All right. And that right there is where that 1 came from. But I can also set this other factor equal to 0, and I could get x equals 0. So I have 2 critical points, one at 1 and one at 0. All right, and of course, this is a parabola, which means it's continuous everywhere. So if the derivative of a function is continuous everywhere, that means there are no places where it's undefined. So in this case, we just have to set it equal to 0. Okay, so again, now once we do that, we set up our table. And then we fill it in. Okay, so right here along this interval row, if we think of the critical points as being those locations where the derivative is 0, where we flatten out the curve, that means I can, if I'm moving from left to right, I hit my first critical point there, and I hit my next one there. Then what I'm going to do is I'm going to create intervals in and around those points in order to gather some more information. So from the left leading all the way up to 0, well, that interval is from negative infinity all the way up to 0. And then I've got between 0 and 1, so that interval is from 0 to 1. And then the next interval I'm going to look at is to the right of 1, so that is from 1 to infinity. Okay, and just like in the last video, what I'm going to do is I'm going to pick different test values inside those intervals to plug into the derivative to see whether or not I have an increasing or a decreasing interval. Okay, so from negative infinity to 0, you can pick any number in that interval. You could pick negative 556, for example, but try and make it easy on yourself. I'm going to pick negative 1. And then for between 0 and 1, I'm just going to keep it simple. I'm going to do 1/2. Ooh, not 1 over 21. Gross, that would be terrible. I'm going to do 1/2. There we go. And then from 1 to infinity, I'm going to pick 2. All right, now you don't want to pick uh, a value that is on the interval, right? You don't want to pick 0 and 1 here because, once again, those are going to be your critical points. So they're not going to tell you much information. Other than that, the derivative is 0. And so the graph should be flat. Okay, so with these test values, I'm now going to plug them into the derivative. And I really only care about the sign that I'm going to get, but I'm going to go ahead and show you what the whole process looks like. So if I figure out, well, what is f prime of -1, my first test point? Remember, I'm going to take -1 and I'm going to plug it into this function right here. So I'm going to have 3 times -1 squared minus 3 times -1. And what I'm going to get is -1 squared is 1, so this is 3. And then I have a -3 times a -1, so this is plus 3. And I'm going to get 6. So f prime of -1 is equal to 6. All right, and I can do that with all of my test points. So for this next one, I have 1/2. Right, so I'm going to do f prime of 1/2. It's going to be 3 times 1/2 squared minus 3 times a half. 1/2 squared is a fourth, so this is 3/4 minus 3/2. If I think of 3/2 being the same as 6/4, I have 3/4 minus 6/4. This is -3/4. So f prime of 1/2 is equal to -3/4. Okay, and then finally, I can do my last test value. I can figure out what f prime of 2 is. So I'm going to do 3 times 2 squared minus 3 times 2. 2 squared is 4. 3 times 4 is 12. And then let's see, this is minus 6. So I'm going to end up with positive 6. All right, and once again, like I said, I really only care about the sign of each of these values because whether or not it's positive or negative is going to tell me how my function is behaving. Okay, so for this first one, for f prime -1, I ended up with a positive 6. So that means positive, my function must be increasing. Okay, for this next one, I ended up with a -3/4. So my function must be decreasing. And then finally, I ended up with a positive 6 again. So my function must be increasing on that interval, just like that. Okay, and last, I can do some conclusions here. So to go from increasing to decreasing, 0 must be a maximum value. And to go from decreasing to increasing, 1 must be a minimum value. All right, now once I have all that information, I can kind of think through and begin to sketch what this curve might look like. And I'm just going to do a rough sketch, but before I do that, I might want just a little bit more information. I might want to know the actual value of the function at 0 and the actual value of the function at 1. All right, so if I plug in 0 into the original function, I'm going to get 0 cubed minus 3/2 times 0 squared. I'm going to get 2. So that tells me that the function should pass through the point 0, comma 2. So I should be going through that point there. And then if I plug in 1, okay, I'm going to get 1 cubed, so 1 minus, this is 3/2 times 1 squared, so I'm going to minus 3/2 and then plus 2. Okay, and if I do that, I will get positive 3/2 or 1.5. So I know that at x equals 1, the value of my function is about 1.5. So right there. Oops. All right, and then I can sketch this curve now. All right, so I know I am increasing until I hit this point, and then I decrease down to the next point, and then I go back up. So it might look something like that, which makes sense. It's a cubic function. Okay, let's look at the next problem. Now, you're not always curve sketching. Sometimes you have an application of the first derivative test. So in this case, if you all remember particle motion, I can use the first derivative test to describe how a particle or an object moves along an axis. All right, so remember this is the position function. First, I need to figure out my critical points. So I'm going to take the derivative of this function. And remember, the derivative of position is actually velocity. So this is going to tell me the speed of my particle. All right, now you've got a quotient here. So this is quotient rule. Remember, you're going to do low d high. So we're going to do t squared plus 1. That's the bottom. Times the derivative of the top. So this is going to be times 8. And then minus high d low. So keep the top, take the derivative of the bottom. Looks like that's 2t. And then that's all going to be over the bottom squared. And I'm not going to write that out. I'm just going to leave it like that. All right, let's go ahead and simplify this a little bit. Going to go ahead and distribute. All right, and I'm going to end up with, looks like 8t squared plus 8, and minus, this is 16t squared. And then I still have that bottom part of my fraction. So I know the velocity function is equal to 8 minus 8t squared all over t squared plus 1 squared. Okay, now I can use this velocity function now to find my critical points. And remember critical points, this is where the function is equal to 0 or it's undefined. So let's do the easy part first. Let's figure out where this is equal to 0. So to do that for a quotient, you really just have to figure out where the top is equal to 0. Because if the top is equal to 0 and we divide it by a number, 0 divided by a number is 0. So I'm going to set 8 minus 8t squared equal to 0. And I'm going to get, let's see, 8 equals 8t squared. And then I'm going to get 1 equals t squared. So t should equal the square root of 1, which is plus or minus 1. All right, now I could also figure out where this function is undefined by setting the denominator equal to 0. But if you think about it, the denominator is really, really close to the denominator of the original function. And remember, a function is undefined if its denominator is equal to 0. So if this one is undefined, and the denominator basically matches the original, then wherever those undefined points are on the velocity, they're also going to be undefined on the position, which means the particle can't move to those points. So I'm actually going to ignore the undefined part, and I'm just going to say plus or minus 1 is my critical point. Okay, so now that we have my two critical points, I can set up my table real quick. So if I think through, my first critical point is at -1, my next one is at 1, then what I'm going to do is set up this table, and in the first row, remember we're going to look at my intervals. So if I look at the interval of the function all the way up to -1, all right, that's going to be from -infinity to -1. And then I look at the interval between -1 and 1. And then I look at the interval to the right of 1. So this is 1 comma infinity. Okay, I'm going to test some values. So the values I'm going to test need to be inside each of these intervals. Let's see. So for this first one, I can test -2. For this second one, I can test 0. And for this third one, I can test 2. Remember, you're just picking values inside the interval that are going to be easy to plug in and work with. Okay, now I'm going to take -2 and plug it into this derivative. So this is going to get a little ugly here, so I might do this off to the side. Let's see. The velocity at -2 is equal to 8 minus 8 times -2 squared all over -2 squared plus 1, and then that is squared. So let's see, this is 8 minus 8 times -2 squared is 4. So I have 8 minus 32 all over, this is going to be 4 plus 1 squared, so this is going to be 5 squared, which is 25. 8 minus 32 is -24 over 25. So the uh, derivative at -2 is equal to -24 over 25. Okay, now I'm going to do the same thing for 0. Figure out what the derivative is at 0. And this one is going to be way easier. It looks like I'm going to end up with 8 over 1, which is just 8. So the derivative at 0 is 8. And then I can plug in 2. And when I plug in 2, you're actually going to end up getting the same thing as -2. Because all those 2's are going to be squared. And 2 squared and -2 squared are the same thing. So I end up with the derivative at 2 is equal to -24 over 25. Okay, and then finally, I can make some conclusions here. So negative derivative means my function is decreasing along this interval. And that would be okay to write, except we're talking about a particle and it says describe its motion. So I want to be more specific than decreasing. I want to say, if you guys remember particle motion, if the velocity is negative, okay, that means the particle is actually moving left. Okay, in the next interval, I have a +8. So this is increasing. So that means the particle is moving right. And then last one, I have a negative interval, so I could say decreasing again. And then we could say moving left. All right, now one last thing to think through. Think about the domain of the function here. So yeah, we just did the first derivative test on this function. And if we were talking about a graph, this would all be great. But because we're talking about real life and real motion here, remember, you can't take negative time. So really, all of this is irrelevant because the interval from -infinity to -1, I mean, that's impossible. That would be like time traveling into the past, okay? And we don't really do that. So what I really want to do is pretend for a minute my function actually starts at time t equals 0, and then describe the motion from there. Okay, I already figured out that the velocity at time 0 is positive, and then I hit my first critical point at 1. So if I was really, really going to do this problem well, I would say the particle moves to the right, from t equals 0 to t equals 1. So for 1 second, the particle is moving right. Then the particle moves to the left for the rest of the time. Okay, we could even go one step further and say a particle is not moving at t equals 1 because it's a critical point. So at that exact moment, the particle has actually stopped its motion. All right, very good. I know this video is a little bit longer. That's because the first derivative test has a lot of parts. But flipping over to the back now, we got two more problems to figure out. It says use the first derivative test to find the relative extrema. And this is really, really similar to what we just did. You're going to find your critical points, you're going to set up this table, and you're going to use the conclusion from the table to determine whether or not those critical points are maximum values, minimum values, or neither. So at this point, we've done a lot of these tables now between the last lesson and this one. So I want you guys to actually pause the video, see if you can do this problem on your own. I will, as always, give you the solution in 5, 4, 3, 2, 1. All right, I know this is a lot, but first I took the derivative of my function. Be careful, you've got power rule and you have chain rule. So derivative of the outside, that would be this piece right here. And then times derivative of the inside, that would be that piece there. And that simplifies to 4x over 3 times the cube root of x squared minus 4. Okay, now in this case, I want to consider both where this derivative is equal to 0. So that would be right here at x equals 0. That's one critical point. Remember, just set the top equal to 0 and solve. I also want to consider where the function, where the derivative is undefined. So I'm going to set the bottom equal to 0 and solve. And I get plus or minus 2. And I care about this for this one because you just want to double check when you do that second part for the undefined values that they're not undefined on the main function. It's okay if they're undefined on the derivative, but it is not okay if they're also undefined on the main function. So if I plug in plus or minus 2 back into the original, I'm good. All right, and then I set up my table here. So I've got 3 critical points, one at -2, one at 0, and one at 2. And I'm trying to figure out if they're minimums or maximums or neither. So I set up my points, I made my table, here are my intervals, here are my test values, and then you can kind of see off to the left, I tested each one by plugging it into the derivative, and I made a conclusion. Now, for you guys, it's okay if you use a calculator, but I do want to walk you through real quick a couple of these because they're a little misleading. So first of all, when I plug in -3 into the derivative, I end up with a -12 on top and a +3 cube root of 5 on the bottom. So this is negative divided by positive. This is a negative number. That's why it is decreasing on that interval. However, on the next one, it's a little misleading. When I plug in -1, I end up with a -4 on top, but I end up with 3 times the cube root of -3 on the bottom. The cube root of a negative is also negative. So this is going to be negative divided by negative, and I end up with positive. That's why it's increasing. Uh, Same kind of misleading thing down here. Even though I have a +4 on top, the cube root on the bottom is negative, so I have positive over negative. This one is decreasing. And then the last one's really easy. It's positive all the way around. Okay, so on my intervals, I go from decreasing to increasing. So that means -2 is a minimum value. Then I go from increasing to decreasing. So 0 is a maximum value. And then decreasing back to increasing, +2 must be a minimum value. So that's how you would use the first derivative test to find and determine what the relative extrema are. Okay, next problem. It says find the intervals where the function is increasing and decreasing. So really similar. You need to take the derivative, find your critical points, figure out where is it increasing, decreasing. Now for this one, I'm actually going to walk through with you, even though, yes, I know we're at half an hour right now on the video, but this one's a little different because you have a trig function. So the first thing I'm going to do is I'm going to take the derivative of this trig function. So first part, I'm going to have 1/2, and then the derivative of a negative sine x is negative cosine x. So I end up with that. And now I got to figure out where this function is undefined. That is nowhere. Okay. Cosine is a wave that goes on forever and ever and ever. So we're good there. I also have to figure out where this equals 0. So I'm going to take my 1/2 minus cosine of x, and I'm going to set it equal to 0. In other words, I'm looking for wherever the cosine of x is equal to 1/2. Now, the reason I'm going to walk you through this one is because this is very important. It gives us an interval from 0 to 2 pi. If you guys remember your radians and your unit circle, this is asking for all the points along a circle. So 0 is the start of the circle, 2 pi is all the way around the circle. We're looking for every single angle measurement along the circle that gives us a cosine value of 1/2. So that's a little misleading because if you just plug in this into a calculator, it's only going to spit out one value. There's actually multiple, okay? So if I remember my unit circle, I know that the cosine, oops, wrong tool. Cosine is always equal to the x coordinates on a unit circle. So I'm going to go around my unit circle and find all the places where the x coordinate is 1/2, okay? So the first time that occurs, I believe, is at uh, pi over 3, okay? And then that's in quadrant 1. If you jump over to quadrant 2, all the x values are negative, so I can ignore that. Quadrant 3, all the x values are negative, so I can ignore that. And then this is going to happen again in quadrant 4. And let's see, I believe that will happen at 5 pi over 3. Okay, so I now have all of the spaces where the cosine is equal to 1/2. Once again, if you plugged it into a calculator, you would just get pi over 3. You would not get this other 5 pi over 3. So this is really important that you think about this interval here. All right, now these are my critical points, so I can set up my table. So I have one point at pi over 3. I have another point at 5 pi over 3. And when I go to set this table up, remember, I'm going to choose some intervals. So this is from, now again, let's think about this. It's a circle that repeats itself over and over and over. So it might be tempting to say from negative infinity to pi over 3, but what we're actually going to do is set it equal from 0 to pi over 3 because it's a circle, so it loops back on itself over and over and over again. So I can't go any lower than 0. All right, and then for this, I'm going to do pi over 3 to 5 pi over 3. And then for this one, I'm going to go from 5 pi over 3 all the way to the end of the circle, which is 2 pi. Okay, and for my test values, I just have to pick something between 0 and pi over 3. Let's do, I don't know, uh, let's do pi over 4. Why not? Okay, and then between pi over 3 and 5 pi over 3, let's do pi over 2. And then for 5 pi over 3 all the way to 2 pi, let's do 3 pi over 4. Or sorry, not 3, 7 pi over 4. Okay, now I'm going to do my test values. I'm going to plug them into the derivative. So when I do that, I'm going to take f prime of pi over 4 for my first test, and I'm going to plug it into this function right here. So I know it's going to be 1/2 minus the cosine of pi over 4. All right. Let's see. The cosine of pi over 4 is root 2 over 2. So this is 1/2 minus root 2 over 2. We can combine that into one fraction, and I end up with this. Okay, I can do the same thing for my next test point. I have f prime of pi over 2. I get 1/2 minus the cosine of pi over 2. The cosine of pi over 2 is just 0, so this is 1/2. All right, and then for 7 pi over 4, the value of cosine at 7 pi over 4 is actually the same at pi over 4. So when I plug in 7 pi over 4, I'm going to get the same thing as I got up top with my first test value. Okay, so now I'm looking at this, this, and this. All right, again, a little misleading, relies on your knowledge of roots and fractions here. Um, you have 1 minus root 2. Well, root 2 must be bigger than 1 because root 1 is 1. So if we take the root of a bigger number, we must have a bigger answer. So I have 1 minus something that's bigger than 1. This is going to be negative, and this is going to be negative. So I know for my intervals, I know on the first interval, I must be decreasing because my test value was negative. And I know on the last interval, I must also be decreasing. And then for my middle interval, I got a positive 1/2, which means I must be increasing. Okay, so now I know this function, 1/2 x minus sine of x, from 0 to pi over 3, it is decreasing. From pi over 3 to 5 pi over 3, it's increasing. And then from 5 pi over 3 to 2 pi, it's decreasing. And then because it's a circle, it just loops back around and does that again. All right. So really, we would say from pi over 3 to 5 pi over 3, it's increasing. And then from 5 pi over 3 all the way back to pi over 3, it's decreasing. Kind of weird because it's a circle. Okay, last. This should just be a review for you guys, but it's a little tricky because if you are given the graph of f prime and you're told to find all the critical points, this is different than if you're given the graph of f. So on the original graph of a function, if you're told to find the critical points, you're looking for where the slope is 0 or undefined. That is different if you're given the graph of f prime. If you're given the graph of f prime, I just told you what you're looking for. You're primarily looking for where the slope is 0. So in these types of problems, the critical points are not the hills and the valleys. The critical points are actually wherever wherever the graph hits 0. Because if this is a graph of the slope, you want where the slope, the value of the slope, is at y equals 0. So in this first one, I have 3 critical points. All right. And I also kind of want to look at the slope in and around it, right? So if I think of this as my boundary line, everything above that line meant that the original function was increasing. It's a positive slope. Everything below that line meant the original function is decreasing. It's a negative slope. So here I went from increasing to decreasing. Here I went from decreasing to increasing. And then here I went increasing to decreasing again. Okay, so for this first one, I went from going up to down. That means I have a uh, relative max at x equals -3. Okay, and then for this one, I went from going down to up, negative to positive. So I have a relative minimum at x equals 1. And then here we go from up to down, increasing to decreasing. This is another maximum. And this is at x equals 3. All right, so I want you to pause the video and try it for this other one. I will wrap this lesson up by giving the answer in 3, 2. Okay, so hopefully you said you had a relative maximum at x equals -2 because you go from increasing to decreasing. Hopefully you said you had a relative minimum at x equals 0 because you go from decreasing to increasing. And then there is actually no extrema right here at x equals 2 because we went from positive to positive. So nothing actually happened there. All right. Okay. That's it for this lesson. Sorry, it's a long one, but wanted to make sure you guys were comfortable with the first derivative test.